Welcome to the very first episode of Mastering Java, a course where we don't just learn Java, we understand it from the inside out. Have you ever wondered what really happens when you write something as simple as int h equals 25? To most people, it's just code, but behind the scenes, that one line connects your logic, the JVM, and the physical memory of your computer. In this series, we will break down every concept from variables and data types to the JVM internals through the lens of both Java and computer science fundamentals. So, whether you are a beginner aiming to master Java the right way or a professional who wants to go deeper than surface level syntax, this is the course for you. In today's episode, we will start at the very foundation. What is a variable? What does a data type really do? And how do they shape the way computers see the world? Let's dive in. So, first, why this topic matters? Because variables and data types are the foundation of all programming logic. Every decision your program makes, every value it stores, every interaction with memory begins with a variable of a certain type. Without variables, there's no way to store state. Without types, there's no way to interpret data. Together, they define how software behaves and how it communicates with the underlying machine. And also, they control how memory is used and how data is interpreted. When you declare a variable in Java, you are not just giving a name to a piece of data. You are telling the JVM exactly how much memory to reserve and how those raw bits should be understood. For example, an int uses 32 bits and represents a whole number, while a double uses 64 bits and follows the IEEE 754 standard for floating point numbers. The type determines everything: how the data is stored, how it's retrieved, what operations are legal, and how the JVM optimizes performance. Misunderstanding this can lead to bugs, waste memory, or even system crashes in low-level programming contexts. Also, understanding them deeply means understanding how Java really works. You see, Java is more than just a programming language. It's an ecosystem built on well-defined rules that govern how code is translated into memory instructions, executed by the JVM and managed over time. Variables and data types sit at the heart of this system. When you understand how Java stores a primitive type in stack memory versus how it references an object on the heap, when you know how a bit, an int, and a double are all represented in binary and how the JVM treats them differently during execution, then you begin to see that Java's behavior isn't magic. It's deterministic, logical, and grounded in computer science principles. So, when we say we are learning variables and data types, we are really learning how memory works, how performance is shaped, how code becomes behavior, and how Java design represents deep system level decisions. That's why this topic isn't just for beginners, it's for anyone who wants to write better, faster, more predictable Java code. Alright, let's move on. What first? What is a variable? A variable is a symbolic name for a memory location. That's a textbook definition. But let's unpack what it really means in the context of programming, Java, and computer architecture. When we write int score equals 100 in Java, we are doing three things at once: reserving space in memory, a specific number of bits based on the type. which in this situation int needs 32 bits, accessing a value, in this case the number 100, labeling that memory location with the name score. The word symbolic is key. The variable name doesn't directly point to the physical memory. It's an abstraction. It lets you, the programmer, refer to that location without worrying about actual memory addresses. Behind the scenes, the compiler and the JVM handle address resolution. They map your symbolic name to a concrete memory address, then ensure the correct amount of memory is reserved and the correct operations are allowed based on the variable's type. This abstraction is what makes programming accessible. But understanding the concrete reality underneath it is what makes you powerful. A variable stores a value that can change during program execution. That's actually where the word variable comes from. It's not fixed, it's a named storage location in memory whose content can be updated as your program runs. For example, when you write these two lines of code, int counter equals 0, then counter equals counter plus 1. In this case, the variable counter starts at 0, and then later becomes 1. The name counter still points to the same location in memory, but the value stored in that location has changed. This idea that we can change what's stored under a name is the core of imperative programming. It allows a program to track state, respond to input, and evolve over time. From a low-level perspective, changing a variable means the CPU writes a new value into the memory address that was originally reserved for that variable. The symbolic name stays the same, but the date bits change. This is what makes things like loops, counters, and accumulators possible. Tools that are vital for everything from sorting algorithms to real-time systems, which you can think of it as a labeled box in memory. When you write int age equals 25, the label is the variable's name, age. The size and shape of the box is determined by the variable's data type int. In this case, int is 4 bits, double is 8 bits. And the contents of the box are actually values stored at the point in time, which is 25. So, when you write this code, you are telling JVM, give me a box labeled age, size for an integer, and place the value 25 inside it. And if you later write a code age equals 200, you are simply replacing the contents of the box. The label and the size remain the same, but the value has changed. This analogy helps you visualize something important. The name helps us refer to the value in code. The type tells the machine that what kind of box it is and how to interpret its contents. And the value is what we can change during execution. And most importantly, the box lives somewhere in memory. And you don't need to remember the warehouse address. The system handles that. In Java, depending on the variable type and the score, the box might live in the stack or on the heap. A variable is not just a label, it's a contract. When you declare something like int age equals 25, you are telling the compiler, reserve 32 bits of memory, store the binary equivalent of the number 25 there, associate the location with the name age, and interpret those 32 bits as a signed integer. The variable name is for you, the programmer. The type is for the machine, so it knows how much memory to reserve and how to interpret the raw binary date. So, in short, a variable connects three words. Your logic as a developer. For example, you are tracking users' age, so you declare the variable age. And the compiler and JVM, which preparing the code for execution. Also, the physical memory hardware, which stores and retrieves the data. So, here's what we know about a variable. But why do we need data types? Why not just have variables that can store anything, like a magic box? This answer lies in how computers work at the lowest level. Memory stores only binary, zeros and ones. Data types define how to interpret those bits. At the lowest level, computer memory stores only binary, zeros and ones. That's it. No numbers, no text, no colors or sounds. Just a sequence of high and low voltages, which we represent as ones and zeros. This is crucial to understand because the machine doesn't know what those bits mean. It's up to us, through programming languages, compilers, and data types, to tell the system how to interpret them. For example, the binary pattern 0, 1, 5 of 0 and then 1 could mean any of the could be a lot of things, like the number 25 if it's an int and the character upper letter A in ACID, the beginning of the floating point value, or just raw binary data with no interpretation yet. This is why data types matter so much. A data type gives context to binary data. It says these 32 bits should be treated as a signed integer, or this sequence of bits should be interpreted as a text string. Without this context, the system has no idea how to operate on the data. It can't end, compare, point, or store anything correctly. So, when we declare a variable in Java and specify a type like int or boolean, we are not just choosing a format. We are defining how the machine should interpret raw memory. And also, data types define size, form, and operations allowed. When you declare a variable in Java, you are doing more than naming a value. You are defining how that value lives in memory and how the system should treat it. A data type isn't just a label. It carries three essential instructions to the JVM and the underlying machine. First, size. How much memory to reserve? Every type has a specific fixed size. That's how the JVM knows how much space to allocate. Byte takes 1 byte, int takes 4 bytes, double takes 8 bytes. This directly impacts how values are stored in RAM and how they move in and out of CPU registers. The size determines not only memory layout, but how efficiently variables can be accessed, cached, and passed around during execution. The second, format how to decode the bits. Now that we've reserved the space, the system needs to know how should I read these bits. That's what format defines. The binary pattern's structure and meaning. Take the same bits. They can represent wildly different things depending on the type. As an int, a whole number. As a char, a letter. As a float, a decimal value. As a reference, a memory address. The type acts like a decoder ring. It tells the JVM, interpret these 32 bits using the integer format. Treat these as a IEEE 754 floating point. This is where date types meet digital design. Formats match underlying binary encoding standards defined by hardware. Third, operations allow what you can legally do. Finally, the type controls what operations are valid on a value. You can add two ints. You can concatenate strings. You can compare booleans, but you can't multiply a boolean or divide a string. These constraints aren't arbitrary. They are baked into both the Java language rules and the JVM bytecode operations. They enforce type safety, prevent logic errors, and optimize performance by mapping directly to low-level machine instructions. Without types, date would be meaningless noise. Imagine opening a file and see just a string of ones and zeros, no label, no structure, no format. That's what raw memory looks like to a computer. It has no inherent meaning. It's just electrical signals or magnetic states, depending on the hardware. What gives that date meaning is how we choose to interpret it. A date type is a rule book. It says the group of bits is a number. These bits represent a letter. This sequence points to an object in memory. Without types, the machine wouldn't know how to perform calculations, compare values, render characters on a screen, or even allocate the right amount of memory. The same binary pattern could be interpreted as a boolean, a chat, or a float, and each would produce totally different outcomes. In Java, the type system ensures that the bits in memory aren't treated like noise. It ensures they are treated as meaningful, safe, and predictable values that your program and the JVM can trust. Types give meaning to bits. At the heart of programming is this simple truth. Types give meaning to bits. Computers operate on memory filled with binary values, just zeros and ones. But those bits have no meaning on their own. For example, the same bits array that we used as an example before could be totally different meaning with different data type. It depends entirely on the date type. If we interpret as an integer, it's 65. If it's a character, it's the upper letter A. So it go on. The takeaway here is simple but profound. The bits don't change, the interpretation does. This is why every variable in Java must have a type. Without a type, the JVM doesn't know how to make sense of the bits in memory. You are not just storing date. You are instructing the system how to understand that date. The type defines the interpretation of bits. That's not just a programming rule. It's a deep truth about how computers work. When you declare a variable in Java, the type tells the system how to interpret the raw binary data stored in memory. These two variables will have the same bits like this, but because one is declared as an int and the other as a char, the JVM treats value as the number 65. The letter is upper letter A. That's the power of type. They transform binary into structured, meaningful information. So when we say Java is statically typed, we mean that Java requires this interpretation to be declared up front. That's how it enforces type safety, memory efficiency, and clear, predictable behavior. In short, types are the rules for reading the language of memory. This is what makes programming logic safe and scalable, and what allows Java to build everything from mobile apps to banking systems with confidence. So, how does Java use date types? So far, we'll talk about what date types are and why they matter. Now let's look at how Java uses date types in practice from compilation to execution. Java is statically typed. Each variable has a declared type. That means every variable must be declared with a type, and that type is known and checked at compile time. For example, when you read this code, first you declare the count is a number 10, and then you align the string 10 to it. It will cause the compile time error. The compiler will stop you right there before the program runs because the type system ensures consistency and safety. So, why static typing matters? From a computer science standpoint, static typing has huge benefits. It allows the compiler to catch type errors early. It ensures that memory allocation is predictable. It helps the JVM generate optimized bytecode because types are fixed, and it makes large code base and it makes large code bases more maintainable. Since every variable has a clear enforced identifier. By contrast, in a dynamically typed language like Python or JavaScript, you can write this code. You can first declare the x is 5, then align the string to the x. This flexibility can be convenient, but it also introduces risk since you might not discover a bug until runtime. So, Java's static type system actually do is early protection. Fail early, not late. Type checking at compile time is a guardrail. It prevents errors from silently slipping into your logic. That's why you will always hear developers say, if it compiles in Java, it probably runs. Then let's see the data types of Java more in detail. Primitive types are the building blocks. In Java, primitive types are the fundamental data units, the smallest elements you can use to store values directly in memory. These include get, int, double, char, boolean. Unlike objects, which are complex data structures stored on the heap, primitive types are simple and stored directly in the stack in most cases. Why primitives matter? Primitive types are the building blocks of all other data structures in Java. Each primitive type has a fixed size in bits, represents a specific kind of information, like integers, floating point, numbers, characters, or logical flags, allows for fast, low-level operations since there's no object overhead. Is used as the foundation for arrays, class fields, and calculations. Each of these directly maps to a predictable memory layout, which the JVM and the CPU can work with efficiently. Primitives are different from reference type, which don't hold the value themselves. They hold a reference to a memory location on the heap. But even inside objects, it's usually primitive fields that carry the actual data. So, in effect, objects are made of references and primitives, and the primitives are the items. Reference types use memory differently. So far, we've seen that primitive types store data directly, like putting a number directly in a box, but reference types, like objects and arrays, work differently. In Java, when you create an object or an array, you don't store the actual data in the variable. Instead, you store a reference, a kind of pointer to where the data lives in memory, which is the stack and the heap. Java uses two main memory areas. The stack, fast, short-lived memory for method calls and local primitive variables. The heap, larger, shared memory for objects and arrays. So, what makes reference types different? Reference types can grow and shrink in size, like arrays or object graphs are created using new like a new student in this line of code, can be null, meaning the reference points to nothing. Involve in direction. You access the value through the reference. This allows for more flexibility. Objects can contain multiple fields, methods, or even other objects, but it also introduces more complexity in memory management. There also have a code example to show that reference and value behavior. In this example, you can see if you declare a primitive variable and then align this variable to a new variable. At this moment, it just happened. The value is copied, and the A and B are independent. But when you put a reference typed variable x to y, and then you change one of the item of y, then it will also change the value inside the array x. This is because x and y refer to the same array in memory. Reference types don't copy it, they copy the pointer. This is a huge difference between primitive and reference types. The JVM enforces type rules at runtime for safety and speed. Java's type system starts at compile time, but it doesn't stop there. The JVM enforces type rules at runtime to ensure that your program runs safely, avoids illegal operations, and stays fast and efficient. First, for safety, preventing type errors. The JVM maintains strict running time checks to prevent dangerous behavior like accessing memory through an invalid reference, casting objects to the wrong type, invoking methods that don't exist on an object. The JVM detects this at runtime and through a class cost exception, stopping execution before something corrupts memory. This is type safety in action, protecting your program from unpredictable behavior even after it passes compilation. Speed, enabling optimizations. Knowing types at runtime also allows the JVM to inline methods when it knows exactly what type will be used. Use monomorphic or polymorphic call signs to speed up method dispatch. Avoid unnecessary type checks where types are stable. These optimizations are part of JVM's just-in-time compiler, which uses type information to make your code faster as it runs. Behind the scenes is the JVM uses a typeware instruction set in the bytecode like this for different instruction for different data types. These are not generic operations, they are typed operations. They are typed operations, and the JVM will throw an error if the types don't match. This gives the JVM huge performance advantages. It doesn't need to guess or check types at runtime, but in dynamic languages like Python and PHP or JavaScript, the types are decided on the fly. This adds flexibility but outcomes at the cost of speed, memory, and sometimes safety. Alright, let's take a step back. Why do we need all these types rules in Java, in the JVM, and even in memory? Because everything in computing, from high-level logic to low-level machine code, is built on a core principle. Bits Bits are meaningless without structure. Structure is defined by types. Variables map to memory addresses. Date types determine how many bits are read or write. When you declare a variable in Java, you are not just naming a value, you are telling the system to reserve space in memory to hold that value. In fact, every variable maps to a specific memory address. This is true for both primitive and reference types, though the details different. Think of memory as a long row of boxes. Imagine memory as a long row of boxes, each with a address. When you write this code, x equals the number. I'm too lazy to read. What happens is the JVM allocates 4 bits since an int in Java is 32 bits. Somewhere in memory says at address 1000. The variable x is a name that points to this location. So you can think it looks like just like this. Without a type, the system could misread the memory. This is the actual binary pattern of the number. Trading 4 bits meant for float as an int, or trading to call a method on a number. That's why variables must be strongly typed in Java. When you declare x, the system knows to reserve 4 bits in memory to treat those bits as a signed 32-bit integer, and to use 4-bit CPU instructions. If this system accidentally reads just 1 bit instead of 4, it says 1, just this, which is not the intended value. That's why types must strictly control how many bits are accessed, both for correctness and for speed. Date alignment and cache performance also depend on type size. Let's say your variable lives at memory address 1000. If it's an int, the CPU will read 4 bits, start from 1000. If it's a bit, it will read just one bit from that same spot. Misreading that memory with the wrong type would give nonsense, or worse, crash the system. And more deeper sense is CPUs can read 4 or 8 bits in one instruction. So knowing the exact type lets the JVM and the compiler generate optimized memory operations. The deep principle is CPU instructions depend on date type. The CPU chooses different operations depending on the type of date. Because different date types, this is the instruction set that the CPU would use to operate different date based on date types. Because different date types require different formats, use different CPU instructions, have different routing overflow and precision behavior, and are optimized differently in pipelines and caches. That's why Java's bytecode separates instructions by type and the JVM translates these into the right CPU instructions depending on the platform. Also, at the hardware level, a single variable type like int or float tells the compiler and the CPU how many bits to operate on, what kind of math rules to follow, which registers and execution units to use, and what kind of overflow or routing behavior to expect. Without clear typing, the CPU wouldn't know what to do, or worse, it might do the wrong thing. Java and the JVM are built with these low-level ideas in mind. Everything we've discussed, variables, date types, memory addresses, CPU instructions, may seem like low-level technical details, but here's the truth. Java and the JVM are designed around these very ideas. When Java was created in the 1990s, its designers had a clear goal: build a language that's safe, portable, and efficient, but still grounded in real computer architecture. That's why Java is statically typed to ensure memory safety and predictability. Java's bytecode uses typed instructions. The JVM manages memory and execution just like a real CPU would, but with guardrails. The JVM is a virtual machine, not an abstraction. The Java virtual machine is more than an interpreter. It's a type-aware execution engine that enforces type rules at runtime, translates typed bytecode to machine instructions, allocates memory precisely based on types, performs optimizations like method inline, register allocation, and just-in-time compilation, all based on type info. In other words, the JVM is a real computer simulator and the types are its language of control. Understanding variables and data types isn't just about writing code and that compiles. It's about understanding how your code maps to the machine and how Java through the JVM acts as a bridge between high-level logic and low-level hardware. This is what makes Java scalable for enterprise systems, perform for large applications, and safe by design. Alright, that's today's full content. And now you understand how variable and data types shape memory, logic, and execution in Java. But to truly grasp why types matter, we need to go one level deeper, all the way down to binary. So, next episode, from bits to bytes. In the next episode, we will answer questions like what exactly is a bit? How are numbers, characters, and logic stored in memory? You will see how Java's data types are not just language rules, they are grounded in electrical and logical design of computers. We'll break it all down with visuals and examples. So whether you are brand new or deeply technical, it will all click. Thanks for supporting this video. I will looking forward to seeing you in the next video. Bye.